Fine. So today we will look into TT&C, and we will try and understand as to how this subsystem works. Okay. So what is TT&C? Telemetry, tracking, and control, right? So in order to keep the satellite in a proper place, okay, we need a control center, right? So if we have this control center, it becomes easy for us to monitor and track. So signals can be sent from the base station to, the uh, space, and accordingly it reacts. So we have seen in a lot of concepts previously where if this station keeping, okay, if this satellite is not kept in place, then it is actually going to get into something called graveyard. So we do not need such kind of scenarios. Instead, we have developed robust systems called TT&C, okay, telemetry tracking and control systems, which will actually help us in tracking the sensors and making sure that everything is in place. Okay, so the TT&C subsystem performs several routine functions on the spacecraft. So it's not only just, whenever you want to move it left, right, or whenever you want to just maneuver it, but then also for the maintenance as well. Okay, regular checks, random checks keeps happening to make sure that the device is fine and proper signals are being received, the antennas are in good condition. So all these, routine checks keeps happening, which is automated. The telemetry or telemetering function could be interpreted as measurement at a distance. Okay? So we are at a higher distance, right? Vast distance, and it's very difficult to send up people on space and get things rectified. So instead, what we will do here is through software, through commands, through the control center, we try to get this rectified. In future, who knows? Okay, in future, you might have your job position in space. It might come up. Okay, so things are working out in such a way that, previously, if you just recall around 70, around 100 years ago, okay, we couldn't travel so fast from one country to another country. But then now there are systems in place. We have flights, we have jets, we have helicopters, okay, which can travel at almost the speed of sound and the speed of light, right? So supersonic jets which travel fast, right? So specifically, it refers to the overall operation of generating an electrical signal proportional to the quantity being measured and encoding and transmitting this to a distant station. So the station is not near, it is very far. So it needs to encode the signals. Why do we need to encode the signals? Can someone unmute and tell me why is encoding so important? Yes. Why is encoding so important? Is it really necessary? Students, I'm waiting for a reply. So what happens when encoding is done? Is our signals safe? Right? Yeah. So signals are going to be safe when we try to encode them so that whatever information is being passed cannot be tracked by someone else. So encoding of information is very much important, and data which are transmitted as telemetry signals include the attitude control, okay, then how much the information that we receive from the sensors, right? So one thing that we need to keep in mind is uh, data from sensors are very important. Okay, so it can be with regards to the distance, it can be with regards to the performance, right? So sensors should be of high quality. Okay, there shouldn't be any compromise with the quality of sensors which will be used for tracking. Data which are transmitted as telemetry signals include this information and environmental information such as magnetic field and so on. Right? Okay. Spacecraft information such as temperatures, power supply, stored fuel pressure. Now, why is pressure so important with regards to fuel? Can someone tell me why is pressure so important? Nishmita, can you answer that question? Anybody would like to answer that? As to why is pressure important with respect to fuel?
Like fuel will be present in the space, so for that, like if it is not pressurized, it will be flowing around the
Okay,
storage.
that is one more thing. The other insight, thank you, Krishan. The other insight that I will give you is if you compare your diesel engines and petrol engines, there is one major differentiation between them. What is it? What is the major differentiation between them with regards to spark plug, right? So these petrol engines do need a spark plug, but diesel engines do not need a spark plug. That is because of the viscosity of the fuel and the pressure is built up. So once the pressure is built up, there is ignition that happens. Okay, there's burning of fuel. The process of burning of fuel happens. So pressure, maintaining pressure is actually so much important that too much of pressure can actually start burning the fuel that is being collected. Okay, so maintenance of pressure is of such high importance. And when we are there in space, we cannot expect everything as here on Earth, which is so comfortable, okay, which is so, all fine. But there we have all extreme weathers, as I've told you. Right? Certain frequencies have been designated by international agreements. Okay? Just like how I told you in the last class, we have certain frequencies, for example, for Bluetooth, for Wi-Fi. Okay, we have different versions of Wi-Fi. Right now, Wi-Fi 6 is the latest one. You can actually look up for these specifications on the website or the data sheets. During the during transfer and drift orbital phases of satellite launch, a special channel is used along with omnidirectional antenna. Okay, so we try to design antennas in such a way that everything, the signals, whatever that we are transmitting, should be transmitted without any loss. Okay, so once the satellite is on station, one of the normal communications transponder may be used along with the directional antenna unless some emergency arises, which makes it necessary to switch back to special channel used during the transfer orbit. So we will have some antennas used for special purpose. We will not be using them every time. Okay. So only during the time of emergency, only if something is malfunctioning, then we switch to, yes, it's always good to have a backup. Right? Okay. Telemetry and command may be thought of as complementary functions. Okay. So what is complementary? I think all of you have studied CMOS VLSI, right? What is complementary for digital functions, digital logic for that matter? Complementary. Anisha, what is complementary? Anisha Devi, you're there? Anybody else wants to answer that? Complementary functions. Yes, that's right. So you can find that they are opposite to each other. So if one is on, the other will be off. Okay. So that is what is meant by complementary functions. The telemetry subsystems transmits information about the satellite to Earth station, while the command subsystem receives signals, which is the command signals from Earth station, right? So often in response to telemetered information. So what is happening here? The satellite and Earth station, okay, the command subsystem receives command signals from the Earth station in response to a telemetered information. So whatever information that we send, it sends back through the sensors and through the antennas. So your antennas are to be high performance. Any small change in values, it should be able to pick it up. The command subsystem demodulates and, if necessary, decodes the command signals and routes these to the appropriate equipment needed to execute necessary action. So if you have sent a command, okay, then appropriate things need to work out. So what is the appropriate thing? For example, maneuvering. Okay, so if I have to maneuver it, then I have to take control of my jets, right? So the thrust that happens, this attitude change may be made communication transponders switch in out of circuits, antennas redirected, and station keeping maneuvers carried out of command. So all these functionalities can be done with the help of a command. Okay, station keeping, redirection, maneuvering, which means changing it to left, right, north, south, all that is possible. So it is clearly important to prevent unauthorized commands from being received and decoded. So this is the reason, why we try to encode signals, okay, so that it responds to only us. It doesn't respond to someone else's command. So in that case, in worst case, what is going to happen? We will lose control of our satellite. So once we lose control, then whatever money invested, whatever is the purpose, is all gone in vain, right? So encrypt is actually a Greek word. Okay? So in Greek it is called cryptane, okay, which means to hide something, and represents the process of concealing the command signals in a secure code. Okay, just like how we have Hamming code, you have seen a lot of codes and studied as well, right? Even in your information theory and coding, right? So these encoding techniques are used, and we send our signals to the satellite and make sure that they are hitting the right one. This differs from the normal process of encoding, which converts characters in a command signal into a code suitable for transmission. So not only looking after what kind of code, but also we should make sure that our transmission is efficient. Okay, whatever signals that we are passing is efficient. It should not take up a lot of power. It should not take up a lot of delay, right? So all this are to be kept in mind. Tracking of satellite is accomplished by having satellite transmit beacon signals, which are received at the TT&C Earth stations. So this can be, received at the Earth station. So it's just like, I have another station in space, a replica of what I have at Earth station. Tracking is important during transfer and drift orbital phases. Okay, so what is the drift? Drift is nothing but when it goes off its track. Okay, so when it's not in track, so that's when we call that, the satellite is drifted. Once it is on station, the position of geostationary satellite will tend to be shifted as a result of various forces. So we have seen this a lot of times, right? Where different forces are actually disturbing the normal operation of a satellite. So it can be your atmospheric pressure, it can be uh, the solar winds. Okay, so many such factors. It can be even rain that can disturb the signals when your satellite is transmitting to the earth station. Tracking beacons may be transmitted in telemetry channel or by pilot carriers at frequencies in one of the main communications channel or by special tracking antennas. Satellite range from the ground station is also required from time to time. Okay, so which means your satellite range from ground station is also required from time to time. So we need to make sure that this satellite is actually put in range. It should not go beyond range. If it goes beyond range, then we wouldn't be able to communicate. So we have seen this diagram in the last class, right, where we try to discuss about the block diagram. So you can see that you have your telemetry tracking and command facilities, which has data communications, analytics, controls, and computers. So we have seen this extensively in the last class. So these subsystems actually help us keeping the satellite in place. So the receiving data, the range. So the range also should be kept in mind. Say suppose I place the satellite somewhere here far, then I should be able to transmit signals. It should be able to catch up, right? It can be determined by measurement of propagation delay of signals, especially transmitted for ranging purpose. So we can calculate how much delay is happening. Okay, if I place the satellite in one of the positions, and then accordingly we can take data from that and try and check if there is a lot of delay, then probably we'll move the satellite to a closer range, closest possible range, and try to retransmit and check if there is any delay in the signal. So we compare with the signal 1 and signal 2 and try and analyze if there were improvements in delay. So if there were improvements in delay, the same process is continued. Okay. So telemetry tracking and command functions are complex operations. As I told you, a lot of things are involved. It's not just moving the satellite, but maintaining the satellite. It's like taking care of a baby in space. Okay. So which requires special ground facilities in addition to TT&C subsystems on the satellite. So this diagram that you saw here was a Canadian satellite, a block diagram of Canadian satellite. Right. So today we'll continue talking about transponders. So transponders are nothing but something which is an essential part of our satellite systems, right? Which helps us in transmitting and receiving information. So these are actually the primary contacts for us. Transponder is a series of interconnected units which forms a communication channel between the receive and transmit antennas in communication satellite. Some of the units utilized by transponder in a given channel may be common to a number of transponders. So which means it is like a copy paste. So the antennas will be of the same structure, same material, but it will be placed apart. Although reference may be made to a specific transponder, this must be thought of as an equipment. Okay. So we will see in the diagram, okay, as to how this transponder looks, and you will be able to understand, right? So this is your horizontal polarization, okay, and the the width is about 36, okay. So if you add up 36 to 6105, you will be getting about 6145, right? So this is capable of about 500 such sections, okay. So this is an uplink frequency, okay, and polarization plan, and these numbers are actually telling us how much frequency it is, and the frequency range is in megahertz. The bandwidth allocated for C-band service is 500 megahertz. So the full thing that you saw is about 500 megahertz, and that is divided into smaller sections. Okay, and these sections are nothing but called sub-bands, and each sub-band is used for a single transponder. So which means this one that you see here, okay, is a sub-band, and I will have a transponder here. The other one that you see here is another subsystem, okay, and it will have a transponder. So totally it's about 500 megahertz range. Okay. A typical transponder bandwidth is about 36 megahertz, which I've shown you, allowing for a 4 megahertz guard band. Can someone tell me why is this guard band necessary? You have studied this exclusively in your communication subjects, right? Why is guard band necessary? What's the purpose of putting a guard band? So Haas, can you answer? Why are we using a guard band? So Haas, you are there? Yes, Suhas, I want you to answer if guard band is really necessary and what's the purpose of guard band. You can unmute. You can unmute and respond. Okay, so guard band is actually used for uh, making sure that there is no interference, okay, between the other bands. So it's like a separation that happens. Okay, so because of this, we can reduce noise, interference, and the channel capacity will also be fine. Okay, and the other thing is that we will be able to efficiently communicate. Okay, so that's the purpose of having this guard band. So this is of a range of about 4 megahertz. Okay, 4 megahertz is used for the guard band. Okay, guard band between transponders, 12 such transponders can be accommodated in the 500 megahertz bandwidth. So in this total bandwidth we can accommodate about how many? About 12 transponders. Okay, so you can calculate 36 into 12, and then you can even have this guard band. So accordingly 4 megahertz for each guard band. So by making use of polarization isolation, this number can be doubled. So if I use polarization, okay, then I can actually increase, or I can double this number. So what is polarization? It refers to the fact that carriers which may be on the same frequency but with opposite senses of polarization can be isolated. Okay, so with this they cancel out, and we can actually increase the capacity. With linear polarization, vertical and horizontal polarized carriers can be separated in each way. So linear polarization is used for this, and circular polarization also will be useful. We will see a few problems, okay, in which we will be doing horizontal, vertical, and circular polarizations. Because the carriers with opposite senses of polarization may overlap in frequency, this technique is referred as frequency reuse. So frequency reuse is one such technique where you can actually make use of the same frequency which was allocated to someone else. So by this, what is happening? I can make use of uh, many other resources, okay, and for an efficient communication. So this is my total bandwidth, okay, and these are my subsystems, the Guardband here, okay, and each subsystem about 36 megahertz, all in megahertz, okay. So this is for your C-band type of communication satellite that we saw the diagram. Frequency reuse may also be achieved with spot beam antennas. Okay, so these spot beam antennas, the name itself suggests that the beam that they emit will be in the form of a spot, and these may be combined with polarization reuse to provide an effective bandwidth of 2000 megahertz. So we are actually having 4 times performance, right? We are having 500 megahertz, but we are able to accommodate with the help of frequency reuse up to 2000 megahertz. So this is how your channels look. Okay, as I told you previously, we do have about 12 transponder channels, right? Ranging from 1 to 12, and the multiplexer is used for this functionality, okay, where you will be selecting one of the lines and that will be passed to your output. So that's the function of your mux, isn't it? So you receive from the antenna which is in this range, which is the C-band range, okay, and this will be passed on to a band pass filter. This is the symbol for a band pass. So if there is a line only here in the middle one and there's no slash here on the upper two, then it is called band stop. Okay, so this is the symbol for band pass. So after band pass, okay, so we will see that these are passing through a receiver, okay, a wideband receiver, and then once it passes through the receiver, we are giving it as an input to demux. So demux, this is the functionality, right? Single input and many outputs. So here in mux, the reverse operation, many to one. Okay, so you can find that these ranges, the ranges of input to demux and the output of mux is the same, 3.7 to 4.2 gigahertz. Now we cannot communicate with megahertz, right? So it should happen. All these are gigahertz operation frequencies. Okay, so these are your power gain blocks, okay, that you see in between, and they are equally placed apart. Okay, so you can see that there is about 40. So why is it 40? Because 36 for each plus 4. Okay, so that makes up to 40, and you can see here that these frequencies are added up accordingly. Okay, 40 40 each. So this is an example actually taken for transponder channels. Okay. Yeah. So the figure shows how this channeling is done. Okay, these channeling systems, these frequencies in gigahertz, how they are allocated. For example, 3.720 is given to the first unit, okay, to the first transponder, and 3.7 is given to the second one. Consequently, 4.1 is given to the 12th transponder. So this is how your frequencies in the spectrum is divided, okay, with a range of 500 and 36 for each a subsystem and 4 Guardband, 4 megahertz Guardband, so totaling up to 40. So that's the difference in frequencies that you can see here, right? The incoming or uplink frequency range is this. The carriers may be received on one or more antennas, all having the same polarization. Okay, so if you're using vertical polarization, you'll have to use the same thing. Okay, if you're using horizontal polarization, you'll have to use the same thing. So there is no mixing of polarizations. The input filter passes the full 500 megahertz band to the receiver while rejecting out of band noise and interference such as might be caused by image signals. So we make use of this band pass filter so that that range only is passed. Okay, it's not low pass, it's not high pass, but custom made filter, which is your specific region of interest, which is your bandpass. Okay, fine. There will be many modulated carriers with this 500 megahertz passband, and all of these are amplified and frequency converted in the common receiver. So here that you see, okay, you will have your receiver. Okay, so all these are converted and then passed to your multiplexer. Your demultiplexer actually. So the frequency conversion shifts the carriers and downlinks the frequency band, which is also 500 megahertz wide, extending from 3.7 to 4.2 gigahertz, right? So that is what you see here. 3.7 to 4.2 gigahertz after it passes through a wideband receiver. At this point, the signals are channelized into frequency bands, which represent individual transponder bandwidths. Okay? The center frequencies that we saw. A transponder may handle one modulated carrier, such as a TV signal, or it may handle number of separate carriers simultaneously, each modulated by its own telephony or other baseband signals. Okay. So we will be looking into this diagram. So this is the block diagram that we will be looking into for the wideband receiver. Okay. Now this section that you see here is actually the internal of this. Okay, whatever you see here, wideband receiver. Okay, so internally, this is the circuitry as to how it is. Okay. So you will have an oscillator, okay, which is about 2.2 gigahertz. You will have an preamplifier, a mixer, amplifier, and then it passes through your demux. So whatever you see here, okay, the same thing is a mirror image here. The reason why we do this is because if in case in future, okay, if this one of these spoils, okay, then we can always connect it to a different contact here, and this can be actually used. Okay, so that's the important thing that you can see here. It's a mirror, or it's a copy of the same components. Okay, so this is a section of your satellite wideband receiver. Okay, and here you can see mixer takes the help of preamplifier and your oscillator. It mixes the signal and then amplifies. Now remember, in amplifier what is going to happen, noise and your message both are amplified. Okay, it's not a repeater. Okay, keep in mind. So which means whenever we are passing through, we need to pass proper information. If not, even the noises are amplified. The duplicate receiver is provided so that if one fails, the other is automatically switched in. How do we do this? You have this small contact that you can see here, right? So once this disconnects, it connects to the other section. Okay, so just have a look at this diagram. Okay, so this is your receiver. Okay, as I told you, using this contact, we actually can switch from one section to another section. So this is actually very much important to have a backup, right? Okay. The combination is referred to as redundant receiver, meaning that although two are provided, only one is in use at a given time. So we will be using only one set. Okay, we will not be using both the sets. Only in case of emergency, if one fails, then it is necessary for us to switch to the redundant receiver. Until then, that will not be in use. The first stage in receiver is a low noise amplifier. Okay, so the one that you see here, pre-amplifier, is a low noise amplifier. Okay, LNA. So the amplifier adds little noise to the carrier being amplified. At the same time, it provides sufficient amplification for the carrier to override the higher noise. So as I mentioned, it's a combination of both message as well as noise. So both are getting combined and getting amplified. So when I use an LNA, so it will help me that in such a way that your noises will be less, and then your message signal, maybe you can denote it as M of T. Okay, your message signal will be a higher um, value. And then it is following a mixer stage. Okay, so this is what you see here, a mixer stage. Okay, so in calculations involving noise, it is usually more convenient to refer all noise levels to the LNA input. So all the noise is actually fed into this so that we get the advantage of using an LNA. Okay, fine. And the next thing that we can see here is with regards to your designer, okay, as to how your receiver is done. In a well-designed receiver, the equivalent noise temperature referred to LNA input is basically that of LNA alone. Okay, so it's actually an LNA itself. The overall noise temperature must also be taken into account, added from the antenna. So not only information, but noise also should be taken into consideration. The equivalent noise temperature of a satellite receiver may be on the order of a few hundred kelvins. Okay. So what do we see here? We see that this temperature can also be a form of noise. Okay, so the equivalent noise temperature can go up to 100 kelvins, a few hundred kelvins. Okay, fine. The LNA feeds into a mixer stage, which also requires an LO signal for frequency conversion process. The power drive from LO to the mixer input is about 10 dBm. Now this is dBs, okay, logarithmic value, which actually compares to power signals with reference to 1 milli, yeah. The oscillator frequency must be highly stable and have low phase noise. Okay, so which means the frequency must be very stable. Okay, and it should have a low noise. A second amplifier follows the mixer stage to provide an overall receiver of about 60 dB. Okay, so we have another amplifier that you can see, right? You can see here you have another amplifier. So this is capable of giving us about 60 dB. Okay, so this is important. Okay, the signal levels in decibels referred to input are as shown in the figure. We have seen that. Splitting the gain between the pre-amplifier at 6 GHz and the second amplifier at 4 GHz prevents oscillation. Okay, so this can occur if all the gain were to be provided at the same frequency. Okay, so we should make sure that we as much as possible try to split signals and make the best use of it. Okay, so we will try and discuss the upcoming topics. Okay, which is your input demultiplexer in the next class. Okay, so we just have a last one for planned for today. The wideband receiver utilizes only solid state active devices. Okay, keep in mind whatever used for wideband is only your solid state active devices. In some designs, tunnel diode amplifiers have been used for pre-amplifier. Okay, so the one that you see here, the preamplifier, tunnel diodes are used. Okay, so solid devices are used for these. Solid state active. Okay. So with advances in FET technology, FET amplifiers which offer equal or better performance are now available for both bands. So which means we can use we can take the help of FET, and we can try and advance the technology. In some designs, tunnel diode amplifiers have been used, okay, and the parametric amplifiers at 14 gigahertz in 12 gigahertz transponders. So diode mixer stages are used, fine, and the amplifier following the mixer may utilize even BJTs. So not only FETs, but we can make use of BJTs for your 4 gigahertz and FETs at 12 gigahertz. Okay, so FETs for a higher frequency and BJTs for a lower frequency, which is about 4 gigahertz. Okay.